You're probably sick of everybody talking about the AI revolution. But funnily enough, most scientists aren't talking about it enough. To this day, most science is done through rigorous amounts of trial and error. Make one molecule, see if it treats a disease, then redesign that molecule if it needs to treat more effectively. In a lot of cases, these processes are done one at a time. But why? Now, it might be because there's a lack of data and some of these algorithms aren't accurate yet, but others claim it's because scientists aren't using these AI tools correctly. Luckily, this new paper published in Nature is trying to show us how to do better. Complete computational design of high-efficiency chem elimination enzymes combines different well-known AI models to design over 1,000 new enzymes. And through several rounds of optimization, they then went into the lab and made those enzymes that were over 100 times more effective than the current standard. It wasn't about designing new algorithms, it was about using them correctly. So without further ado,
science that's cool, papers so unique.
Welcome back to
Cool Ass Papers that I read this week.
Like with all cool ass papers, we have to take a look at the background of this paper, see what the problems in the general field are and how these authors tried to solve them. Let's throw it back to high school for a second and talk about enzymes. Enzymes are proteins that are biological catalysts. They speed up the rate of a specific chemical reaction that happens within our cells. And each enzyme works something like this. A substrate moves into this little pocket, known as the active site. Binding to the active site causes the enzyme to move ever so slightly to change its shape, yielding a transition state, which is very important in the journey to catalyzing a reaction. So important that we'll be talking a lot about this transition state later, so just hold tight. As the enzyme transitions, it creates the perfect environment for the two substrates to interact with each other in a way that doesn't usually happen. The enzyme lowers the activation energy of this reaction, which is the initial energetic barrier that prevents the reaction from happening. In this example, everything yields two products, as one sad face binds to the red happy face chain, leaving one less sad face in the sad face chain. Both products then leave the active site, making the enzyme free and ready to bind to another substrate. In summary, enzymes are like Hinge. Sure, you might meet the love of your life at the grocery store as you both reach for the same avocado, but you might be waiting in the avocado store for quite some time. Hinge just helps to speed things up a bit. Without enzymes, many of the biological processes that happen in our bodies every single day wouldn't happen. They're absolutely essential to our cells. And each enzyme is specific to a certain type of reaction. The active site can only bind to the substrates needed for that reaction. Because of how specific they are, enzymes are often described as a lock and key mechanism. Personally, I like to think of them a lot as me at my first summer job. Really good at making the sandwiches that I was hired to make, but don't ask me to go back there and restock stuff. That wasn't what I signed up for. Now, before we go any further, we need to define two parameters that quantify enzyme performance. The first is the Michaelis constant, or Km. This is a measure of affinity, how tightly the enzyme can hold onto or bind to that substrate. The mathematical representation and formal definition can be confusing, so we don't have to worry about it for this video. But it is important to know that a lower Km means that it binds tighter to its substrate. So in this case, a lower Km means a better enzyme. The second parameter is known as the turnover number, or catalytic rate constant, kcat. This is defined as how fast this enzymatic reaction occurs, and it's generally measured as the number of molecules that the enzymes can process per second. Unlike Km, a higher kcat means that an enzyme is hustling and working really quickly. So a higher kcat means a better working enzyme. We're gonna hear these two terms a lot over the rest of this video, so make sure you're getting cozy with them. Km, kcat, Km, kcat, Km, kcat, Km. There are many natural enzymes, such as the ones you would see in glycolysis or the Krebs cycle. But there are many unnatural ones too, so these are the ones that scientists will go into the lab and actually make. And they're often referred to either as synthetic or de novo enzymes. And these two terms will be used interchangeably throughout the video. The goal of these synthetic enzymes is to improve the performance of their natural counterpart. That would mean decreasing the Km and increasing the kcat. These changes can be done all over the enzyme, whether that be in the active site itself or other non-reactive parts of the enzyme that allow it to fold properly. But we'll get to that a little later. Rather than making single amino acid changes, isolating that enzyme, then praying that those changes worked, AI algorithms and other computational methods can be used to allow scientists to predict how this new synthetic enzyme will behave. And since it takes a really long time to isolate an enzyme, enzymologists can save lots of time and money by predicting what changes are needed to make a more optimal enzyme. So why isn't AI used more often to screen how new synthetic enzymes will perform? The problem is that current computational methods have been poor predictors of how synthetic enzymes will behave. There are a whole slew of reasons outlined in this paper, but most notably, a lot of the changes that are made in the active site change the overall enzyme structure too much to function as intended. As these authors mentioned, notably, catalysis is extremely sensitive to molecular details, and shifts of the catalytic constellation by just a few degrees or tenths of an angstrom, which would be 10 to the minus 11 meters, from optimality may translate into orders of magnitude decreases in efficiency. You know when you're trying to make your bed and you are putting on the tight fitted sheet, so you attach the first corner to the bed and then you walk on over to attach the second sheet, but the first corner flips off? It's like that. They list a whole slew of other issues, such as low stability and expressibility of enzymes that are designed this way, and not accounting for certain amino acid interactions that might be very important for catalytic efficiency. Put simply, current research in making de novo enzymes has gone to plan, but the plan's been kind of off. It's like you're trying to build a house, but you get the blueprints to McDonald's. Sure, you'll have all the essentials like a kitchen and a bathroom and a commercial-sized ice cream maker that's always out of order, but there isn't really a great place to put a bed. So here's the exciting part about this paper, trying to do things differently. These authors applied the enhanced computing power of AI to parts of de novo enzyme design that were previously unrefined. And they did this by combining several commercially available algorithms. First, they took a single family of enzymes, known as Kemp eliminases, and used an algorithm to identify thousands of different backbones that were promising in previous research. Then they used a different algorithm to stabilize this transition state, known as the theozyme, in their theoretical enzymes. Told you we'd come back to the transition state. Finally, their AI optimized parts in and around the active site. After all this computation, they took the most promising designs and actually made them in the lab to see how accurate their AI was at producing a fully functioning, highly improved synthetic enzyme. They would then go back to their computational stuff to continually make further tweaks to get the best enzyme that they could. Their overall goal? They state that unlike previous approaches, the workflow emphasizes stability across the entire protein. Their working hypothesis is that effective enzyme design demands control over all protein degrees of freedom and not just one or two of these factors. Our overall goal as big old nerds on YouTube is answering the question, did this actually work? It was time to put their money where their pipettes were. The first step was to apply their first large analytical model to a class of enzymes known as Kemp eliminases, which catalyzed the reaction called, you guessed it, Kemp elimination. It's not super important how this reaction works or what it does, but it is super important to know that it's a completely synthetic enzyme. There's no natural enzyme that can do what Kemp eliminases can do. And this is a smart move for them right now because it allows them to only compare within de novo enzymes. Keep the scope narrow for now, expand it later. Now here's where things start to get really impressive. Their model of many options yielded 73 most promising designs. But designs are just one thing. So they went into the lab to actually make 73 enzymes. If you've ever had to make an enzyme, you know just how painful this is. Every process is slightly different, but in general, you have to grow cells in a dish, break apart those cells to retrieve their proteins, and specifically isolate only the proteins and enzymes that you want, purify them intensely, and then analyze their structure to prove that you have the one and only enzyme that you are actually planning to get. This often takes days, and is even more time consuming if you have a lot of impurities or you get the wrong enzyme. The fact they made 73 unique enzymes, all of them multiple times, is good enough reason for me to get into nature. Of these 73, only 66 of them were actually stable for further experiments. They did a couple initial studies, but found that of the 66, the two with the best, Km and kcat, remember how tightly the enzyme binds and how fast that enzyme works, were chosen for further analysis. These enzymes are known as Des27 and Des61. Although promising, it was a little unfortunate that these two best performers still performed not so great. Des27 and Des61 were several orders of magnitude worse than other Kemp eliminases that were designed through wet lab only practices, so ones that did not need any AI algorithms, which made them the perfect subjects for the next round of optimizations. In both Des27 and Des61, they made 5 to 8 tweaks to very specific amino acid sequences in and around the active site. These tweaks were modeled using one of the best known algorithms for doing so, known as func_lib. Again, we don't really need to know the specifics of what func_lib, just know that it exists and that it made all the difference. This second round of fine-tuning DES27 and DES61 showed up to a 70-fold increase in catalytic rate. Specifically in DES27, they reached a kcat over km of over 12,000 per molar second, and a kcat of almost 3 per second, which is a whole order of magnitude higher than the other enzymes that were designed through AI. Now, although Kemp eliminases are synthetic enzymes, they are based on a natural enzyme. But what's funny about all of this is that their most recent round of tweaks that they made through func_lib made these synthetic enzymes so unbelievably different from the natural enzyme family that they were based off of. In fact, the most similar sequence was still off by around 140 amino acids, meaning that they shared less than 45% of the same sequence. You ever play sport for a while and think, damn, I'm getting really good at this. But then you play with your friend who has 45% less experience, but they are 70 times better than you? It's like that. But how their algorithms know this? And more interestingly, which point mutations actually made the difference into making a more active enzyme? To answer this, they modeled the movement of each amino acid in the active site with molecular dynamic simulations. You guessed it, more computational experiments and predictions. And in these images, each rod and corresponding alphanumeric code represents a different amino acid. So by mapping out where each amino acid is and how they could possibly interact with each other, they could get an estimation of what's actually going on. Specifically, they looked at their most catalytic enzyme they made, DES27.7, and compared it to the first iteration of DES27. They found that the newest version was able to have a more flexible active site, less crowding when the substrate was actually bound, and there was more space for water to enter that active site, which is a very important part in actually catalyzing Kemp elimination. Speaking of DES 27.0, it spent about 63% of the time not bound to the substrate. So like me in my summer job in high school, it spent 63% of the time doing absolutely nothing. Meanwhile, DES 27.7 was on their grind set, only being unbound 12% of the time. Now that sounds like a whole lot of mumbo gumbo, but the gist is that the very specific changes that were outlined through func_lib not only increased the km and kcat of this new enzyme, but they could actually map, model, and identify why those new changes were making the improvements that they made. Now, if I'm being honest, there is a whole lot of mumbo gumbo in this paper. Very cool gumbo, but very dense gumbo. X-ray crystallography, melting temperature and stability of these enzymes, mumbo gumbo. I highly recommend reading this paper if you are into the mumbo nitty-gritty gumbo. Link in the description and in my bio through my link tree. But there's one more thing we haven't really discussed yet. Remember the thiozyme? That transition state thing that is apparently super important to stabilize, but most people don't focus on stabilizing it. The same transition thing that we haven't really talked about in a while. They identified two specific mutations. In both cases, these mutations were not on the active site and were only used to stabilize the thiozyme. First was replace an aspartate at the 162nd amino acid with an alanine. Removing this aspartate completely abolished the catalytic activity of the enzyme. Literally zero, unable to catalyze the reaction. That means that this aspartate is 100% necessary to stabilize the thiozyme and therefore the enzyme as a whole. The second mutation was phenylalanine at position 113. They replaced it with a leucine. When I tell you I was shitting bricks, this one simple change increased the kcat over km to 123,000, and the kcat itself was 30 per second. Are those numbers good? Yeah, they're good. These mutations together made this enzyme 10 times better than the previous best enzyme they could make. 10 times! Making it over 100 times better than other de novo enzymes designed by AI. Take all this together, we can learn some very valuable things. Notably, by stabilizing amino acids that are not in the active site, we're able to increase the catalytic performance of the enzyme, which is amazing because the active site is known to be the main driver of catalysis. And altogether, this gives a lot of credence to these researchers who have been saying that previous models weren't modeling the most important parts of de novo enzyme design. You understand how good that is? Like after all of this, right? All of the different AI algorithms and computational studies and different simulations for atomistic representations and whatnot. And then they had to go in and make all of these different enzymes in the lab and having to isolate every single one and showing that after all of this, they can improve the catalytic ability and have this perfect barrier. Well, so if it wasn't obvious, I really like this paper. Like, a lot. So let's relive the glory days with a quick summary of what happened. These authors strategically combined several AI algorithms to screen over 1,000 different enzyme designs that could potentially improve the catalytic ability of synthetic, or de novo, enzymes. And unlike other computational studies for designing enzymes, they considered the whole enzyme, including parts outside of the active site. They used an algorithm that would best simulate each part of the enzyme. Of their many designs, they isolated and purified over 65 different enzymes. The sequence of their most promising enzyme, DES27, was further optimized using their superior algorithmic workflow. This optimization yielded an enzyme with unprecedented catalytic performance, showing a perfect marriage of dry lab, AI modeling, and wet lab enzymology research. Now, personally, I hope that this is just the beginning, and that hopefully all fields of wet lab research can get as in tune with using AI algorithms to design their experiments. If you think far enough ahead, think of how many treatments we can design and make if we're not stuck just making one thing at a time and instead can design and screen a whole bunch of different ones. Instead, you can just simulate them as accurately as possible and only make a few of the promising designs. With Nobel Prizes in physics and chemistry going to AI-based research in 2024, and now with this paper, it seems like many researchers are on the AI/wet lab hype train. In a perfect world, this should progress science in a way that is way faster than what we're currently doing with these one-at-a-time methods. If you learned something today, be sure to give this video a like so that the YouTube algorithm can push this video forward to other nerds like us who might also like to learn something. If you learned a lot today, be sure to subscribe so you don't miss the next cool-ass paper. Cool-ass paper that you can suggest if you leave a little comment below. Any papers that you may have read recently or heard of and you think would be worth doing a little deep dive into, just leave them down below. But that's all for today. See you later, nerds.